Again, welcome to our April Science Speaker Series at the Mariah Mitchell Association. Thank you all for joining us this evening. It is my esteemed privilege and pleasure to introduce to all of you this evening Dr. Joshua Redding. And tonight's talk is titled Dark and Quiet rather, Astronomy in the Age of Satellite Constellations. This talk and presentation tackles a really timely and surprisingly complex issue, how the rapid growth of satellites is changing not just space, but our ability to study the universe and make decisions about it responsibly. We're very lucky to have Dr. Josh Redding this evening. Josh is an optical astronomer by training and now works as a radio spectrum manager, bringing together science, technology, and policy in a really unique way. He earned his Bachelor of Arts in Astronomy, Physics, and Philosophy from Colgate University and his Master of Science and Doctorate in Physics from UNC Chapel Hill, where he studied unusual white dwarf stars formed from stellar mergers, essentially failed supernovae. Beyond his research, Josh has also worked hands-on with astronomical instrumentation at major observatories, and more recently has moved into science policy. He served as a North Carolina STEM Policy Fellow and was selected for the AAAS Science and Technology Policy Fellowship, where scientists contribute directly to federal decision making. Tonight, Josh will be sharing how astronomers are responding to the rapidly changing space environment and working to ensure that science still has a voice in how we use and manage space. Please join me this evening in welcoming Dr. Josh Redding. Welcome, Josh.
Thank you so much.
We
All
got
right, am I good to go ahead and share my
You
slides?
are all good,
Great.
and I am here shall you need me. Turning
All
it over
right,
to you.
sounds great. All right, just 1 minute. All right, excellent. Well, thank you, everyone, so much for coming out to listen to me tonight. I hope you learned something interesting. So, like Janelle said, I am an optical astronomer by training, and now I have found myself via a long and winding road into the world of radio spectrum management. I'm sure many of you don't know what that is, and I honestly didn't before about September of 2023 either. And now it's what I'm doing for my career, it seems. It is a very interesting world. Like Janelle said, combines science, technology, policy, a lot of cross-cutting issues, and has very consequential decisions being made for things that you do every day. You may not be thinking about how much you rely on wireless communications every day, and it is a big policy exercise to keep all that stuff in working order. Since ending my AAAS fellowship, I got to work at the National Science Foundation in their electromagnetic spectrum management office. Now I am working for the Aerospace Corporation, which is a federally funded research and development center, supporting, via research, simulations, policy, recommendations, things like that, general operations of the federal government. And I'm in the Spectrum Engineering and Policy Office, so I've continued straight on from my work at NSF, now more broadly addressing radio spectrum management at the federal level. But my heart remains with the astronomy field. It is, I think, a very important indicator of the health of the radio spectrum, given its unique needs. But before I get ahead of myself, I'm just going to jump into the presentation. As I'm sure that many of you listening are aware, as astronomy enthusiasts, we are in kind of a new era in terms of space operations. The number of active satellites orbiting the Earth, especially in low Earth orbit, has absolutely exploded in the last decade or so. There are currently about 15,300 active satellites in low Earth orbit. Just 7 years ago, though, there were only 900, so over an order of magnitude increase in less than 7 years. And just to really hammer the growth home, 6 years ago that rose to 2,600, 3,900, 5,200, 7,400, 9,400, and then over 11,000 just over a year ago. You'll notice that those deltas between these numbers are all kind of getting bigger too, creeping out of the below 2,000 range into the 2,000 range. And then just in the past year, over 4,000 new active satellites have been launched. So the pace is only quickening. Astronomers affectionately refer to this plot underneath here as the hockey stick plot, just given the shape of it. But that slope on the end of it, as the time axis keeps going forward, may become even steeper, which is a bit of a scary thing to think about. And it's important to note that this is very largely being driven by satellite communications, and especially Starlink, who were kind of the first to the game. I really can't say that they don't keep themselves busy. They have a very strong move fast and break things mentality, and that's given them control of two-thirds of those active satellites that are in orbit right now. And they don't plan on stopping anytime soon. I'm sure many of you saw this January that SpaceX filed with the FCC for a million satellite orbital data center that they hope to deploy. This prompted a significant response from the astronomy community that I will talk about later. And there, you know, and I wouldn't necessarily take just this application being filed as evidence that it will eventually happen. There are a lot of complicated factors that surround this constellation proposal that may not necessarily make it feasible. But anyway, the point is that this is largely being driven by Starlink, and but there are a lot of other companies who are ready to come in their wake and add to this growth as well. And this is not to say that what Starlink is doing is not valuable. It's absolutely valuable. These are real testimonies from comments submitted to the FCC on some matters that arose out of Starlink filings. And you can see that, you know, Starlink service going into places that previously were not well served by networking, including rural Appalachia, rural Alaska. It's really made a difference in their lives, offering you know, remote learning and remote work opportunities, giving people telehealth options. You know, I like the anecdote here about having to drive to the library parking lot to get any internet access to do homework. So it is absolutely valuable what these satellite communications companies are doing. The thing that needs to be taken into consideration, though, is that this growth has to happen sustainably, right? Space sustainability is becoming a bigger and bigger topic, both domestically and internationally, and it has a lot of components to it. But basically, it's the recognition that with the development of the space environment accelerating, you know, moving as quickly as it is right now, we need to make sure that we don't create damage that is either significantly impactful to people, you know, living their everyday lives, or potentially permanent, or both. So there are a number of elements that fall under this umbrella of space sustainability, including the radio frequency side of things, the quiet part of dark and quiet skies. Everyone is aware of the growing optical issue, which, along with space traffic management, are kind of their difficulty increases directly just with the number of satellites that are in orbit, and the environmental impacts of increased launches, increased deorbits, things like that as well. These all I like to include all of these subjects under this umbrella topic of space sustainability that's very much at the forefront of space policy making right now. So the goal of my presentation today is to kind of give an overview of how space policy is discussed, decided both at the domestic and international levels, and where astronomy fits into that conversation. I will note that most of what I talk about is going to focus on the radio side of things because that has the most formal policy infrastructure surrounding it. So there's a lot more to talk about in that area, but I will describe these other three subjects as well, where they stand right now and where they're going into the future. So I have you know, kind of a choice of whether to start domestically and then go internationally, or start internationally and then go domestically. I'm going to do that second option because the international policy framework is kind of the foundation for domestic policy. And I'll mention this later, but in terms of enforcement of regulations, that only happens domestically as well. So kind of setting the stage is what the international community does, and I will start there. share with this overview of space policymaking. So the two main bodies where space policy is discussed internationally are the International Telecommunication Union, or the ITU, and specifically their radio communications sector handles everything to do with radio spectrum management. And then for everything in the use of space that is not having to do with the radio spectrum, the UN Committee on the Peaceful Use of Outer Space handles that, or the UN COPUOS. And I'll talk about both of these groups in the coming slides. I'm going to focus first on the radio side, though. So just to kind of set the stage of what radio spectrum management is and why it's important. People don't think about the radio spectrum this way, but it is a limited natural resource. There are only so many frequencies in the radio spectrum that can accommodate use of wireless services, and everybody needs to be able to share the spectrum and coexist and not cause each other interference. You can kind of think of the radio spectrum like real estate. Everybody wants to grab their piece of land that will let them do whatever function they want to do with it, but you can't have people, occupying each other's land or blasting signals into other territory where they aren't authorized to do that. So making sure all of that fits together is a very complicated exercise because there are a lot of different radio communication services looking to share the spectrum. From things that you might use every day for, entertainment, all the way up to critical communications, things like, your cell phone service, TV broadcasting, fixed wireless locations, your Wi-Fi, but things like navigation as well, your GPS signals, military applications, satellite communications, all these things need to share the radio spectrum and coexist. And also in this, very crowded pond of players are the science services. We need to conduct science to have access to spectrum, whether it's in an active sense, if you're conducting an experiment and you need to send and receive signals, you need to have access to spectrum to do that. But also, if you want to just measure the natural world, whether it's Earth or the cosmos, you need to be able to see through, all of these cross cutting beams of other services that are trying to provide their service as well. And under the science services is, of course, radio astronomy. Radio astronomers are trying to detect radio signals from distant cosmic sources, just some of the examples of radio astronomy subjects pictured here. And on the left is the Green Bank telescope, the 100-meter dish in Green Bank, West Virginia, in the National Radio Quiet Zone. In order to see these astrophysical phenomena to conduct radio astronomy, you need to have really, really sensitive antennas because these are, billions of light years away potentially, and the signals that are received at Earth are incredibly faint. So this is why I kind of hinted earlier that I feel like radio astronomy has a very unique role as kind of the barometer for health of the radio spectrum, because we have the most sensitive instruments. And if interference starts to go out of control, or the kind of sharing guardrails that keep everybody coexisting break down, radio astronomy is going to see it first. The signals that we're trying to see from space are basically like you trying to see a candle a mile away when someone 10 feet away is shining a spotlight in your face. So it's one of the most technologically intensive services to try to protect, just because of its sensitivity and the needs of actually conducting the service. So that interference comes in the form of radio frequency interference, as I kind of just described, as other transmitting antennas are putting their beams down on the ground. There's the risk of those beams creeping into radio astronomy dishes, or in the same frequency bands that they are trying to observe at that given time. So this plot on the right here is actually from one of the National Radio Astronomy Observatory's regular RFI scans around 2020 and 2021. So this band, this 7.3 to 7.4 gigahertz band here, I will note is not allocated to the Radio Astronomy Service. So, it's clear looking at this that prior to 2020, astronomers probably could have used this band to take observations. But after 2020, somebody switched on use of this band, and now it's completely washed out by the interference that you see here. So astronomy can't happen here anymore effectively. But it is important to note that this is not a radio astronomy allocated band. So no malfeasance is being done here. Under the regulatory framework that I'm about to describe. So while it is unfortunate that astronomy tries to observe wherever it can, because we can't necessarily predict where physics is going to appear, trying to fit that under a formal regulatory structure is a challenge in and of itself as well. This is what the field of radio spectrum management tries to address, is making sure that everybody can coexist in the 275 gigahertz of spectrum that are regulated that are allocated to specific services. This is what the allocated radio spectrum looks like in the United States. All of these different color boxes that comprise this mess of puzzle pieces fit together are all the different radio communication services, and radio astronomy is in here as well. I'll note some important radio astronomy bands that are interesting within this here. Another thing that I haven't yet mentioned that's important to keep in mind is that science services are unique in that we can't really choose the spectrum that we want to use for our services because physics determines the spectrum that we need to see. So, for instance, the 21 centimeter neutral hydrogen line, this is an emission line that comes from hydrogen in its ground state when its electron changes its spin flip, and it emits a very weak signal at 21 centimeters, and this is in the 1400 to 1427 megahertz band. Ideally, if a galaxy is not at all redshifted, then we would see this line here. But of course, the universe doesn't always follow the rules it's supposed to follow. But still, this is why radio astronomy gets the right to use this band, is because this is where this very important feature that you can use to measure the rotation curve of a galaxy and infer the presence of dark matter is in this band. So this is why this band is allocated to radio astronomy. And then another one that I wanted to point out is this 10.68 to 10.7 gigahertz band. This is where you will sometimes see variations in a more continuum spread astrophysical signal. So it's not like a single spectral line. This is where you'll see the actual full curve of the emission from the object moving up and down. So quasar outbursts can cause this. These happen in this 10.68 to 10.7 gigahertz band. And you may notice that right next to it, these kind of light purple bands are allocated to the fixed satellite service operating in the space to Earth direction. So in a band right next to where we are trying to conduct radio astronomy observations is the most used band by satellite services for downlinking their data for transmitting from satellites down to Earth, which is pointing in the wrong direction, right? The radio telescopes are looking out to space and the satellites are beaming down to Earth in just adjacent frequency bands. So this is the band that gets the most focus in terms of coordination with satellite operators and making sure that astronomy can continue to operate, because there is a lot of traffic going in the wrong direction right next to it. So, like I said, at the international level, this difficult exercise happens under the auspices of the ITU. It's actually the oldest UN agency in that it predates the UN by quite a bit. It was founded as the International Telegraph Union back in the 1860s, and then was only folded under UN auspices when that was created in the wake of World War II. And its prime function, or at least the radio communication sector prime function, is to produce and revise the ITU radio regulations, which are a binding UN treaty. There are some 200 countries that engage in the ITU that sign on to the radio regulations and adopt those rules into their domestic rules. To varying degrees. Like I said, it's up to the individual nations as to how radio regulations will be enforced within their borders. But I'll come back to that a little bit later. So, in the radio regulations are all of those allocations for radio frequencies, as well as studies, sharing compatibility studies, all of the technical background that explains why these regulations are in place and how services should coexist. It also coordinates satellite orbits to a degree, largely in geostationary orbit, which I'll talk about later. This new growth of low Earth orbit satellite constellations is really stressing the ITU's ability to coordinate satellite orbits, but I'll talk a bit about the space traffic management issue later on as well. Determines telecommunication operational standards. So there's a lot of, very foundational work that happens under the ITU as well. And studying new technologies and means to expand access as well. There's a whole development sector under the ITU that's looking at the practical uses of spectrum and where it'll go in the future too. So this is what the ITU radio communication sector looks like in terms of being divided into all of the different components that make up radio spectrum management. So you'll see that there are some really kind of fundamental ones in study groups 1 and 3, how to do spectrum management as an exercise, as well as radio wave propagation. So that underlies how sharing compatibility studies are done, and all of the other study groups that focus on actual services. And then the other study groups are focused on those biggest services. So study group 4 is satellites, study group 5 is terrestrial use of the spectrum, study group 6 is broadcasting, and study group 7 is the science services. And under the science services, radio astronomy has its own working party 7D. And that is, for the most part, where astronomers and the NSF Spectrum Office, the National Radio Astronomy Observatory, everybody who has a stake in protecting radio astronomy spectrum engages is in working party 7D. So the way that the ITU works is surrounding the World Radio Communication Conference, or WRC. This is held every 4 years, and at this conference, they will close out whatever work was done over the past 4 years, write everything up into a new version of the radio regulations, and everybody signs on to it. And they'll also think about what are the next pressing issues that the ITU should take under consideration for the next 4 years, or even looking out 8 years to the upcoming World Radio Conference after that. In between the World Radio Conferences, everyone returns to their working parties and does all the work that needs to be done to answer the various agenda items that are chosen at the WRC, write up their findings and all that. And then it begins all again 4 years later at the next one. So the U.S. delegation to this is led by the State Department, though much of the actual work and preparation is done by the FCC and NTIA, two other federal agencies that I'll talk about in just a bit. But like I mentioned, ultimately, it's nations that determine spectrum regulations within their borders. So while it's nice to engage here and make sure that, for instance, U.S. interests are properly represented in the development of the radio regulations or new agenda items, the U.S. has to participate in this process, but in terms of actual enforcement back home, that may not necessarily happen. So looking forward to the next World Radio Conference, Work 27, I wanted to point out that there are actually 4 agenda items that are very pertinent to the science services. It's one of the biggest workloads that science has gotten in quite a while in the ITU. So, agenda item 1.15 is looking at radio communication in the lunar space. We're thinking about going to the moon, potentially having permanent settlements on the moon, and it would be a real shame if we just recreated our congested Earth spectrum environment on the moon as well, especially because the moon has a lot of really unique characteristics that make it valuable to the science services. The one in particular I'll note is the shielded zone of the moon. So I'm sure most of you know that the moon is tidally locked to Earth, which means that its rotation period and its orbital period are about the same. So we always see the same face of the moon pointing towards us. That means that the dark side of the moon, the backside, is shielded from everything on Earth by an entire moon worth of rock. So it is one of the most pristine, quiet zones that is feasible for us to reach and potentially install infrastructure on. So it is actually currently written into the radio regulations that the shielded zone of the moon should be protected for science services. But this may not necessarily extend to the orbit around the moon. The space in between the moon could impact that too. So still a lot of questions to be asked there. Very forward-looking agenda item, this 1.15, and radio astronomy is definitely making its voice heard there. 1.16 is looking at radio quiet zones. So historically, this has been handled domestically. We have the National Radio Quiet Zone in West Virginia in the U.S. that has been around since the 1950s. This agenda item was looking at how can we take all of these radio quiet zones and somehow fold them into ITU international regulations. It's proving to be quite a bit of a challenge, this one. Very procedural. I don't think it's really even gotten into any significant technical contributions towards this particular agenda item because everyone's just fighting about the scope of it at this point. So we'll see where that one goes. It's obviously a big threat to satellite operators to have some way to coordinate large geographic areas where no emissions are allowed. So that one's getting a lot of pushback expectedly. Then 1.17 is looking at space weather sensors. I honestly haven't been following this one too closely, but we got to measure solar activity as well. It's also impactful on satellites as they're trying to conduct their operations in orbit. And then 1.18 is looking at kind of high frequency operations for both radio astronomy and the Earth Exploration Satellite Service, which is the passive science service that's looking at the oceans, climate, or other Earth-related scientific data. So like I've mentioned, it's not necessarily the case that domestically the ITU rules are adopted exactly. So this here is a slice of the table of frequency allocations, that big kind of puzzle plot that I showed a few slides ago, but spelled out more explicitly textually here. So you'll see on the left is the international table. That's the one that the ITU maintains. I highlighted region 2 because the world is separated into 3 regions under the ITU, just to a little better coordinate local operations of the radio spectrum. So region 2 is the one that includes North and South America. And over on the right is the US table, the regulations that are under or that are in enforcement in the US, which is split into federal and non-federal, and you'll see that there are services allocated over in the ITU that are not here in the US, and it's often the case vice versa as well, that we may assign use to something that's not recognized internationally too, and it's fully within our domestic agency's purview to do that. So this is the bridge over to the domestic side of spectrum management, where the actual impactful stuff on enforcement within the US happens. So handling of domestic spectrum management is bifurcated between 2 federal agencies. The FCC, whom most of you have probably heard of, handle the commercial side of spectrum use. They also license companies to deploy the equipment that is going to use the spectrum. So satellite launch licenses need to be approved through the FCC for commercial carriers like Starlink, Amazon, OneWeb, AST SpaceMobile, all of them go through the FCC for all of their work. And then the federal side of spectrum is handled by the National Telecommunication and Information Administration, or NTIA, who you may not have heard of. They are under the auspices of the Department of Commerce, and every federal use of spectrum reports up to them, from military to science services, NASA, NOAA, NSF, all report up to NTIA as well. And then the FCC and NTIA have to work together to make sure that spectrum is shared appropriately between the federal and non-federal services too. And these don't happen in isolation. It's not only NTIA and FCC people engaging in conversation regarding domestic spectrum management. Inputs from all of the federal agencies are important because everybody has different needs, different risks in spectrum use as well. And that is all done through the IRAC, or the Interdepartment Radio Advisory Council. It is more or less kind of a virtual roundtable. It's not literally a table where one person from every agency sits around it, like in this picture here. There are lots of people representing most of the federal agencies, contractors as well, who listen in and participate here. And this is kind of the forum where everybody on the federal side, at least, can hash out their spectrum needs and forward this up to NTIA, who then take it as the consolidated federal position to discuss with the FCC, and then ultimately what becomes actual regulation. So the science services, like I mentioned, live under NASA, NSF, and NOAA. And the IRAC also has a number of subcommittees that address various aspects of spectrum management. It'll also have ad hoc groups that talk about pressing issues, like coordination with our national neighbors, things like modernizing the NTIA manual, which is just a reference that everyone in the federal spectrum sphere uses, and then lots of things regarding novel uses of space that are kind of breaking the current regulatory structure, like a lot of what SpaceX does. There have been a number of IRAC ad hoc committees made towards SpaceX as well. So that is largely an overview of radio spectrum management. It is very complicated, and it's probably the most important exercise you've never heard of, and it's a very interesting place and to engage in. And astronomy, I feel like, has a very interesting role in the spectrum management conversation. So now turning over to the other aspects of space sustainability that I mentioned, and I'm kind of going to group together the optical interference, space traffic management, and environmental impact side of things because, like I mentioned before, these are all kind of directly proportional to how many satellites are in orbit right now. So optical interference, as most people know, is caused by reflection of sunlight off of the mechanical components of satellites, usually their solar panels. That are reflected down to Earth like a big mirror, and we can see them either with our naked eye or in our telescopes. I'm sure everyone has seen this picture on the right before from the Blanco telescope down at CTIO, which is pictured. I think Blanco's the one in the center there on the bottom left. I never actually used Blanco. I used SOAR on the next mountain over. But I wanted to note that while this image looks pretty bad in terms of the streaks that are going through it, this was during an orbital raising maneuver for these Starlink satellites. These are Starlink streaks, so it is not necessarily the case that you will have these dense clusters of satellite streaks going through your images all the time, though it probably will start to look more like this as more and more satellite constellations are deployed, and that number that I showed on the first slide keeps getting bigger. And then, as there are more satellites in the sky, it becomes harder to coordinate all the traffic between them, making sure they don't crash into each other. And those increased launches are going to have, more rocket fuel injected into the atmosphere, rocket stages burning up as they re-enter, satellites burning up as they re-enter the atmosphere and are disposed of. So, these are the things that are the kind of the least defined right now, in terms of scientific data that's looking at their impacts. At least, for the environmental impact side, and how the injection of all of these elements are impacting the atmosphere. For instance, the papers that are always brought up are from like 2022 and 2023, so still very new issues that are being figured out here, all proportional to how many satellites are in orbit. So to set the stage here, I want to talk about orbits just for a little bit. There are kind of three orbital regimes that are always talked about in the context of satellites. There's low Earth orbit, which is arbitrarily defined as below 2,000 kilometers or so. There's geostationary orbit, which is very specific at 35,786 kilometers above the surface of the Earth. It is that specific because that is the orbit at which the satellite will complete an orbital period in the same time that the Earth rotates, so 24 hours. And this means that satellites in geostationary orbit will remain fixed above the same location on Earth all the time. This has obvious benefits for certain services. So GSO is kind of its own regime. LEO and is the one where everybody is launching satellites right now, and then everything in between is called middle Earth orbit, or sorry, medium Earth orbit. I feel like I've heard middle Earth orbit too, but there are no hobbits living there. And That one's a little bit more odd because with it being such a large range, it's kind of hard to define a use case here sometimes. And thinking about how to dispose of things from here is difficult as well. I did get a little ahead of myself. Like I mentioned, geostationary satellites are fixed above their Earth terminals, but everything below that is going to be orbiting faster than the Earth rotates, so they need to be dynamically tracked by Earth terminals on the ground. So as it relates to astronomy, we're thinking about more satellites going up. How bright are they going to be in our images? How quickly will they transit our images? It may be a little counterintuitive, but actually, the lower in altitude satellites are, the better it is overall for optical astronomy. You'd think that they would be brighter being closer to Earth, and they are. But the bigger thing to take into consideration is imagine on this slide here that the sun is beaming its sunlight in from the left side of the slide here. The shadow that's cast by the Earth takes up a bigger fraction of lower orbits than it does orbits that are farther out. So this means that, at twilight, satellites are going to be very bright in the sky. And there are certain science cases that really need to be done at twilight, and calibrations are often done at twilight as well. So it's not to say that, twilight can just be sacrificed in the name of protecting things more broadly, but it does help at least protect the darkest parts of the night when a satellite spends more time in the Earth's shadow. So, once the satellite crosses into Earth's shadow, it'll spend more time there for lower altitude orbits, and there will be less interference to the darkest parts of the night. So that's why it's a little bit better for lower altitudes, and astronomers have been pushing that in the policy sphere as well. The industry is largely following this request at putting things in low orbit. The other thing about low Earth orbit that's advantageous is you're closer to Earth, which is where the equipment that you're trying to connect to is. So you have, stronger links between your satellites and your ground stations if you're a satellite operator. It also provides the more convenient disposal option of putting the satellites back into the Earth's atmosphere where they will burn up. And Constellations are becoming more kind of cheap and disposable in terms of the equipment that they use, but that also means that better technology can be put into them, and the service will improve as well. Just to show, I mentioned that there were just over 15,000 active satellites in orbit now today. As you can see, the vast majority of those are in lower LEO, below 600 kilometers or so. Very few are in upper Leo for those reasons that I just mentioned. There are a number of reasons why it's more advantageous to be closer to Earth. The problem, though, is that in less orbital space, if everybody is throwing all of their satellites into the same fairly tight orbital area, that the risk of collisions is going to be higher because everyone's trying to share a smaller space altogether. So, like I mentioned, excuse me, the choice of orbit also impacts how you're going to dispose of satellites when they reach end of life. Lower Leo, the clear option is to re-enter and burn up in the atmosphere. If you're in geostationary orbit, those satellites tend to be pushed out just a little bit past GSO into what's called a graveyard orbit. So there are a lot of kind of non-functional satellites out past geostationary orbit that probably go all the way back to some of the first satellites that were ever launched in the mid 20th century. But Upper Leo and Mio, it's a bit tougher to think about how to dispose of those because you either have to try to deorbit through all of those Lower Leo satellite constellations that are all crossing over each other. It's like trying to, play Frogger and run across the highway as fast as you can. Or they'd have to transit potentially 30,000 kilometers of space to get out to graveyard orbit, which requires having a lot of fuel on board, and that's not easy either. So that's another reason why kind of Upper Leo and Mio tend not to be as used for service. The biggest use of Mio that I've seen is for satellites acting as relays between geostationary orbit and low Earth orbit. So the companies will have satellites deployed in all of the orbital regimes, and the Mio ones are kind of the connection point there. But it's not often that those are used. There are a number of potential environmental considerations with both of these disposal mechanisms of pushing things out and effectively creating permanent space debris or having them re-enter the atmosphere and whatever that's going to do to the atmosphere with the injection of all those metal, black carbon particles, all that kind of stuff. Like I said before, that study is that field of study is kind of in its early stages still, so it's not fully understood. But that doesn't stop astronomers from raising it as definitely an issue that should be studied at the very least in the near future before it becomes out of control. And then in terms of the space debris side, the doomsday scenario that everybody talks about is Kessler syndrome. So this was theorized by, I think his name was Donald Kessler, a NASA scientist in the 70s, who imagined that enough satellites could be deployed in orbit and they could be so close together such that a single failure of a system that cast off debris would hit another satellite close by. That would break that satellite and create more debris, which would cascade off and hit more functioning systems, and so on, until you have this cascading effect that effectively could take out everything that's in Earth's orbit and send us back to the pre-space age, which would be absolutely disastrous. And this is something that astronomers invoke quite a lot as well, alongside the optical astronomy issue, because it's not only these single big satellites that are a problem for astronomy data; it's the creation of small debris as well. You could think of a cloud of tiny metal shrapnel from a satellite as like a dispersed cloud of tiny mirrors that are all going to reflect some degree of sunlight down to Earth. So the ambient background glow of the sky will increase as more space debris is generated as well. And this is definitely an issue that is at the forefront of policymaking right now. And it's been an issue for a while. I have a little paragraph here from a U.S. National Research Council paper from 1995 that way back then, when there were probably a couple hundred satellites in orbit, if even, that two orbital bands at about 900 to 1,000 kilometers and about 1,500 kilometers altitude were already had already been believed to have exceeded their critical density such that they are effectively in a Kessler scenario. scenario. So the debris that is in these two bands is self-proliferating. At least that was what was found in this paper back in 1995. Now there are over 15,000 satellites in orbit. So this is something that needs to be greatly taken into consideration. And it is the UN COPUOS that tends to handle all of these at the international level. It operates under the Office of Outer Space, or the UN Office of Outer Space Affairs, or UNUSA. This is the group that produced the Outer Space Treaty in 1967, which is kind of the foundation of all space law right now. It's a nice document. It kind of has a lot of high level, kind of platitudes, general principles that space operators should live by, but it's hardly anything enforceable like the radio regulations. The UN COPUOS has two subcommittees: its scientific and technical subcommittee, which is a lot where a lot of astronomy talk takes place, and the legal subcommittee, which thinks about the practical implementation of the guidance that the UN COPUOS develops. So I was very happy in 2024. I got to attend the STSC, and in that meeting, the STSC agreed to adopt this agenda item, and then later that year, the full COPUOS agreed to adopt a 5-year agenda item called "Dark and Quiet Skies: Astronomy and Large Constellations Addressing Emerging Issues and Challenges." So this is now the first time that optical astronomy is being discussed in an international forum, diplomatic forum. I won't call them a policy-making forum because they just produce guidance, but at least the conversation is happening, and there is a lot of attention being dedicated towards it right now. So optical and space sustainability more broadly, as it pertains to astronomy on the domestic side, kind of happens on a pro bono basis. I guess maybe pro bono is not the right description. To kind of give more of the foundation for this, so the FCC, like I said, they license space launches. When operators want to launch a constellation of satellites, they go to the FCC, and the FCC has to approve it, subject to input from other potentially impacted parties. The FCC's regulatory purview largely relies on just radio spectrum related matters. So a satellite could be launched that is not providing a radio communication service, and it could be for really any purpose. And the FCC would have no reason to deny it as long as it doesn't cause RFI, which has all sorts of problems associated with it, as I'm sure you can imagine. But the other side of the FCC's mandate is that they need to serve the public interest, which is not very well defined, but it opens the door for impacts on issues that are not in the radio domain being potentially consequential. So under that public interest mandate, the FCC decided that it is in the best public interest to protect astronomy. So right now, the FCC requires that companies coordinate with the National Science Foundation, the Spectrum Office, as part of the conditions of their operating licenses, and that they make a best faith effort to mitigate impacts of the satellite constellations on ground-based astronomy, and report in regularly as to what progress is being made towards that end. And this applies to NASA science missions as well. So I think last I checked, there are 4 formally signed coordination agreements with satellite operators. SpaceX was the first, followed soon after by OneWeb, and then AST, Space Mobile, and Amazon Kuiper signed on last year. And there are more in discussion. So this is a very positive thing that astronomers have to hold on to right now, in terms of making their voices heard as more satellite development happens. So within these coordination agreements, just some examples of what they contain. The radio side is largely uninteresting, following the radio regulations and domestic rules as they're written. The domestic rules have more specific references to U.S. astronomy infrastructure. So the National Radio Quiet Zone and the Puerto Rico Coordination Zone are still mentioned. And there are specific radio astronomy sites that are mentioned in domestic rules as well. Avoiding main beam illumination of radio telescopes. And then these coordination agreements are meant to be a two-way effort. It's not just the operators making concessions on their end to try to fix things. Astronomers make an effort too. So astronomers developing data processing and technology solutions to mitigate RFI is part of this as well. I'll note that a really successful example of this happened recently, where astronomers at the National Radio Astronomy Observatory or specifically out at Green Bank developed what they call an operational data sharing system in cooperation with SpaceX. And they published a paper on this back in, I think it was August of 2024, that had both NRAO scientists and SpaceX representatives in the author list. And this system is an API that effectively broadcasts where the telescope is pointing at any given point in time. And the satellite operators can read that information and then do something on their end to mitigate their beams being pointed down into the radio telescope. So they may point away if their satellites are capable of steering like that, or they may switch off entirely as they pass overhead. And this was incredibly successful. Starlink actually is able to provide service to all but 3 cells, Starlink size cells, right around Green Bank Observatory in the National Radio Quiet Zone. So actually or something like 99.5% of the people who live in the National Radio Quiet Zone could get Starlink service without it hurting the observations out at Green Bank. And then the optical side of things are largely based on the outputs of 4 conferences that happened in 2020 through 2022. They are probably in need of updating, though it's been a bit difficult to kind of pull an effort together to readdress this. Largely those findings, like this limiting brightness to 7th magnitude, which is about the naked eye limit, came from what would completely saturate the detector on the Vera Rubin Observatory, which is the next big infrastructure project for optical astronomy that was to come at the time, just recently opened in the past year. So, if the satellites were brighter than that, then it would find that there would be nonlinear effects on the detector and that data could not be recovered by any means. So that's where that request came from. But the issue is that that's not really well defined for the operator's side. Is it a limit that they can never exceed, or is it a limit that they need to meet on average? So a lot of ambiguity, things that should really be readdressed at some point soon. Limiting orbits to low altitudes, both for that better impact on astronomy I mentioned before, and so they deorbit on human timescales. Trying not to reflect directly at Earth. Everybody has been thinking about reflect orbital lately, I'm sure. Providing precise telemetry to inform observations, so not to look at this patch of sky at this point in time because there will be satellites passing through it, and then astronomers developing technology on their end as well, just like the radio side of things. But space traffic management and things like reporting that telemetry becomes really cumbersome when you have to do it on a case-by-case basis and be talking to the companies directly. And space traffic management is something that's going to impact everybody worldwide. So really there needs to be a central repository for that information. And this is another place where the US government has been making some strides. So historically, space traffic management was managed under DoD auspices, Department of Defense, because they were largely the users of space as military purposes. So they had a website called spacetrack.org that would report out telemetry on about a 12 to 24-hour basis. That's not great, especially for these new low Earth orbit constellations that are passing overhead much quicker. And now that we're moving from hundreds of satellites to tens of thousands of satellites, mostly commercial, it really needed to be moved out of their responsibility. So the Office of Space Commerce was set up under the Department of Commerce, and their big product that they've been developing and I think is almost ready to be deployed is called TRAX, the Traffic Coordination System for Space. It's basically going to be an improved version of spacetrack.org. And while I was at NSF, we had some conversations with them talking about how astronomers could contribute to this tool and use it to avoid interference. So that is the big overview of all of the policy space. But I wanted to touch back just briefly on that FCC mandate to serve the public interest, because this is where the broader astronomy community comes in and can be most effective. You know, it's the federal agencies make their voices heard through the IRAC. The commercial side has the FCC, and but they also need to listen to the general public as well, especially as not only larger and larger numbers of satellites are being deployed, but satellites are being deployed that are conducting activities in space that have never been done before. And I'll come back to Reflect Orbital on this. For those of you who may have or who aren't aware of them yet. Reflect Orbital is a new company that filed for deployment of a pilot satellite with the FCC for their system that is effectively a constellation of space mirrors. They want to intentionally reflect sunlight down at Earth. I think initially as kind of a supplement to solar farms operating at night. They say that their reflections are going to be as bright or brighter than the full moon directly under the satellite in the center of the beam, which is not great for astronomy. Questionable as to whether they will achieve their operational goals with that. But they also envision potentially a constellation of all these things, doing things like lighting up concert venues as well. The applications they anticipated are going to expand beyond that solar model. So that, along with the SpaceX Million Satellite Orbital Data Center proposal, were both disastrous for astronomy in different ways. And it's through volunteer efforts like this committee that I have up on the slide here, the American Astronomical Society's Committee for the Protection of Astronomy and the Space Environment, or AAS Compass, that astronomers are really making an impact in those conversations. So Compass did recently put together formal petitions to deny both of those applications, the SpaceX Orbital Data Center and Reflect Orbital. And they replied to those, and we submitted replies again as well. And now it's kind of in the FCC's hands. But this was accompanied by a large public comment campaign or co-organized by AAS and Dark Sky International, which is another Dark and Quiet Skies nonprofit organization. And ultimately, to the SpaceX Orbital Data Center, there were 1,500 public comments submitted and 1,800 towards Reflect Orbital, which was just amazing to see because it's a non-trivial effort to submit these comments. You have to make an account on the FCC website, write your comment, and submit it through their forum, which is a bit opaque as well. But it's that that loud voice of the public that really helped give some weight to the petitions to deny that we put forward towards these applications. So we'll see what happens with those in the long run. But astronomers are really starting to pay attention here, and I hope the community does as well. If you're interested in the work of AAS Compass, our link is down there at the bottom. Happy to talk to anyone about Compass as well afterwards, or at some point in the future if you're interested. And that's all I've got. I know, I'm sorry I went over time right up about to the hour, but it was a lot of content to cover. I hope it was interesting.
It certainly was. Thank you so much, Josh. Very, very enthralling. I'd like to kick it to Dr. Malengo, our Director of Astronomy here at Murray Mitchell Association, to just engage in any conversation with you. And I encourage anyone at home, if you have any pressing or burning questions, to just pop them in the Q&A, and I'd be happy to read them to Josh for his answers and responses. Thanks, guys.
First, thank you, Josh. That was very interesting. My fellow from AAAS, NSF. What was it that you said? This was the most interesting topic that you didn't know you needed to know?
Yeah. I had no idea what spectrum management was before I started my fellowship with the NSF. But it touches everything, from, using your cell phone every day to making sure that we can do science.
Yes. So I remember years ago, I don't know if you were at this AAS meeting in Anchorage, Alaska, but we were all put on a bus to watch the movie Space Junk in 3D.
Nice.
Yes. And everybody should look up this movie. You can find it for free on YouTube, Space Junk. I don't know if it's in 3D, but if you have glasses, it's pretty interesting. And that had to have been 15 years ago.
hmm
Really calling people to action about
hmm
these issues, netting space debris and the Kessler syndrome and things like that. And I remember the conversation on the bus on the way back, right, to the conference center. Is there a universal decommissioning plan for all satellites that launch? Like in terms of their reentry and their burn and where they land, which is likely in the ocean, hopefully in the ocean. Um, like when it comes to commercial, government, academic, all of it. Is, I mean, are they required?
Yeah, that's an interesting question. So I do know as part of the FCC filing that a demonstration needs to be made that their risk of generating new orbital debris is below some threshold. I don't remember what it is off the top of my head. And I know that there are criticisms of it because it's more like, any of our given satellites has a 1 in 10,000 chance of, that sounds really high. It's probably, it's more restrictive than 1 in 10,000 because then SpaceX would have like 100% chance of creating one every year or something like that. But I don't think it's that low. But anyway, they have to demonstrate that, the risk of generating debris through collisions is below some threshold. I don't think they really that's probably some component of the disposal that goes into that. But I don't recall ever seeing an explicit disposal plan. And then in terms of the very real risk of dropping satellites in the right place, I have absolutely never seen that, at least in a public-facing forum. It must be something that they handle within the companies on their end, or at least that's my speculation. And we know that they haven't been perfect. You see reports of Starlink debris falling in Canada or North Carolina. I feel like there was another one recently or whatever. So yeah, I don't think that there's a whole lot governing the disposal process right now, unfortunately. And I think it's going to take a lot more of those studies that I mentioned that are kind of in their infancy to really make a case for it. Policy moves slow and these companies move fast. So that's something that makes me very nervous for sure.
So that, I mean, my follow-up to that is it seems that the technology and the need is really outpacing policy and the
Yes.
ability for policy to move.
Yeah, yeah, absolutely. And I've seen kind of the same arguments levered or leveled at academia that, the scientists, if they want to protect themselves, need to keep up. But the response to that is with what resources? We don't have billions of dollars to work with. So yeah.
I have a quick question.
Mhm.
For those of us who aren't astronomers or policymakers, what role, if any, can the general public play in shaping how space is used and how these satellites, how do we interact with them?
Yeah, absolutely. Yeah, I brought up at the end the big public comment campaigns for SpaceX and Reflect Orbital, which were fantastic. And I showed early in the presentation too that the general public comments in favor of the satellite operators sometimes too when it's impactful to them. Those comments that were in favor of SpaceX earlier on. So yeah, like I said, the FCC has public comment periods for its notices of proposed rulemaking and for individual satellite filings as well. It is definitely hard to stay up to speed with all the new developments, especially these days. Things are just moving so fast.
Mhm.
Even those of us who do this professionally have a hard time catching everything that's coming down the pipeline. And on even in groups like AAS Compass that are more formal volunteer organizations dedicated to this, everything just kind of is filtered down through some chain, and everyone is putting this work in, which is significant work on a volunteer basis. The astronomers don't have teams of lawyers dedicated to spectrum management like the satellite operators do.
Mhm.
So it's relying on people to put in the extra effort outside their day jobs to talk about these things that are important to them. I mean, I know that's why I do it. I'm like I showed on the Compass slide. I'm co-chair of the electromagnetic interference subcommittee for Compass. I was the kind of the one who spun up the FCC response infrastructure coming out of Compass. It started with just me drafting everything because I do radio spectrum management, so I was familiar with how to structure those things. And the knowledge disseminated throughout the committee, and we've gotten more experienced at writing these things. And individual people can do this too. I know it takes some effort, but submitting comments to the FCC, they're all read. I've heard that from FCC lawyers directly that they read every comment,
Oh,
and they don't need to be, detailed things. They can just
mhm.
say, "Hello, I am a passionate lover of astronomy, and I care about dark and quiet skies." Tell a little personal anecdote and say, please keep us in mind as you're making your decisions. It's as simple as that. Just a few lines. Of course, it's hard to keep up to speed with things. That's the biggest challenge, I would say. But anybody is welcome to comment on these issues to the FCC.
Thank you, Josh. Would you say, and forgive me if I missed this, are there any promising technological or regulatory solutions that could help balance satellite growth at the rate that it's happening with preserving our dark and quiet skies and, that area of space as we know it?
Yeah, it's tough. It's a tough question to answer because there are so many
Hmm.
facets to it, right?
Right.
So like, Jackie talked about space debris and cleanup
Hmm.
efforts, and there isn't a clear best way to do that. There are lots of
Right.
different proposals for different ways to clean up the space environment. There are a lot of facets that go into the radio operations side of things. Yeah, it's just kind of, and I guess the simplest way I can put it is it's important to be in the room where the decisions are made, because
Hmm.
if your voice isn't being heard, then you're
Right.
not, contributing to the conversation. Yeah, it's got a lot of components, and we try our best to be everywhere that we need to be. It doesn't always work out, but and the resources balance between us and the pro development side is very imbalanced as well. That makes it even harder too. But we're doing our best. And Yeah, and any support from the public will only enhance our voice.
So I would describe that as we're kind of building the satellite as we're positioning it because it's
Exactly,
happening so
exactly.
rapidly.
Yeah.
And I guess just, to close out, Susan, I see that you asked if this presentation will be available to share with other interested parties on YouTube or some other way. So absolutely. So this will be recorded, and after we edit it down just for the beginning and end, we will email it to everyone who has participated this evening, and it will then be available on our Science Speaker dedicated webpage, and we do upload it to our YouTube. So I just wanted to address that really quickly. And to wrap with looking ahead 10 to 20 years from now, what are your biggest concerns and what gives you the most optimism about the future in astronomy in this new and evolving and rapidly changing space environment?
Excellent question. I think my biggest concern is just at the rate at which commercial development is outpacing policy's ability to respond to it.
Hmm.
I don't know how things are going to go. I feel like, looking at the history of policy making in general, that it often takes a disaster for people to finally get up and act on something, and that scares me for the use of space. So I'd say that's my biggest fear right now. In terms of optimism, though, the fact that so many of these operators are coming to the astronomy community and are willing to work with them to figure out solutions like the SpaceX NRAO operational data sharing. And I didn't mention it during the presentation, but SpaceX kind of proactively developed a darkening coating for their satellites that they then offered to market to other operators if they wanted to use. Um, I wouldn't say it was like super effective, but it's a nice gesture that they're trying to do it. So I hope that the response from the astronomy community needs to be, appropriately addressing how serious the problem is, but also open to collaboration with satellite operators, because we're not going to be able to do this alone. The fact that they're paying attention to us is a huge benefit, and
Hmm.
they could if they wanted, just ignore us and continue sending up satellites without paying attention to astronomy at all, which would be terrible. So that kind of collaboration that I'm seeing, I hope that continues into the future. That's my biggest optimism point.
Excellent. Jackie, did you have any thoughts before we formally wrapped for the evening?
I don't know that I could address this any better than Josh could. So I'm grateful for your time, Josh. That was really educational. I know as an astronomer, I think about these large survey telescopes like Rubin,
Hmm.
the Rubin telescope, and perhaps at some point it's North American, or sorry, Northern Hemisphere equivalent, and that at some point that tension between, you know, the efforts of the scientific community and then people who care about dark and quiet skies for different reasons, that's just going to come up and just
Hmm.
butt right up against like a brick wall with some of these other efforts. And so, um, I don't know. I hate to think of it as a cost benefit ratio, but at some point it's a cost benefit ratio.
Hmm.
So I'm grateful that there are people like you and this entire committee, right?
Hmm.
Compass and people on the international stage thinking about things that, I mean, most of us blissfully go every day and don't think about, but are grateful that other people do.
But
So,
it impacts us, right?
yeah.
Hmm.
Largely.
So
Yeah.
thank you.
Josh,
Yeah.
are there any questions we didn't ask you that you hoped rather that we did ask that you wanted to address in summary?
I'm sure there are many, many more questions that could be asked, but I think this was nice and comprehensive. Keeping it at a high enough level, I could talk about spectrum issues for days, but I will spare you from that.
Fair. I'm just so, fascinated and curious as to
Yeah.
like noise and interference of data.
Yeah. Hmm.
So that we can do that offline for sure, but that's something
Yeah.
that definitely, crops up for me.
Hmm.
But on behalf of the Mariah Mitchell Association, Dr. Malengo, and myself, I just wanted to extend another just heartfelt thank you for taking your time this evening to share your presentation with us, as well as what you've been working on and what you're so passionate about. And I just also want to thank you for the work that you're doing to inform policy and to, you know, like Jackie said, the things that we get the benefit of just not thinking about in our day-to-day lives, that you're
Hmm.
playing such an important role in helping shape that space. So from for all of us on, planet Earth, I'm gonna say thank you. But
Thanks so
on
much.
behalf
I
of Marian Mitchell
appreciate it.
Association, we thank you, Dr. Redding, for a fascinating look at how something as vast as space is becoming a place where human decisions truly matter more than we
Hmm.
recognize, and where thoughtful stewardship is more important, especially now than ever. And thank you, everyone, for joining us this evening. As I mentioned, the recording will be edited just for lag time at the beginning and will be made available on Mara Mitchell's YouTube channel, and we'll share it with everyone who attended this evening. Thank you, Josh. Thank you, Jackie. I appreciate you both. Of
Thanks so much for having me.
course. And just so that you know, I have to kick everyone out before the webinar doesn't allow. So guys, I am going to kick you out just so that you know. Not you guys, but everyone else.
Say hi to the DMV for me, Josh.
Will do. Will do.
I want to stop recording.